Okay, we started section 10.5 last time, and we had encountered three formulas that are really all the same formula. They looked like this. The one that we will be using primarily is the one that's boxed in, but they're just versions of the same thing, three versions of the same thing. And we talked about the fact that sometimes, instead of finding something directly, it's easier to find something that's not true and then subtract the options. So the example that we had done was this one. And so we had talked in section 10.3 about the number of ways certain kinds of hands of cards could come about. And this question asks us that we wanted to find at least have at least one card in our hand that's not a club. So if we actually found this directly, we'd have to find the number of ways of getting one club. We'd have to find the number of ways of getting 4 clubs, because that's not all clubs, because 5 of them would be all clubs. The number of ways of getting 3 clubs, the number of ways of getting 2 clubs, the number of ways of getting 1 club, and the number of ways of getting 0 clubs. And we'd have to add all of those combinations together, right? It'd be a bunch of things to add. So instead, it's actually easier to think about what's not, or wanting to not have happen. In fact, we want to not have all clubs. So that's the complement. It's the opposite, or the negation, right? Some different language that we've used in different places throughout this semester. We don't want all clubs. But it's easier to find how we get all clubs. In fact, we found back in section 10.3 how we got all, I think it was diamonds when we did it, but it was found the same way. We had 13 to choose from of our clubs, and we need to choose all 5 of them. And it tells us at the beginning on this particular one, not always in all the problems, how many ways of getting just any general thing to happen, 2,598,960. And in particular, we had seen that again back in section 10.3, and so I didn't want to repeat the process. Now, when you do other problems like these, you may have to calculate that quantity too, right? So you might have actually had to do this first part. This first part, if we'd had to do it, would have been looking like 52, choose 5. That's what we did. 52 of any cards, choose 5 of any of those cards. That would have given us the 2 million number. And then we subtract off choosing all clubs. So this is the way this is working. So we're going to take a look a little bit more. Again, I like to keep a little bit of our focus similar or the same so that we can change a portion of it and see how that affects things. So you're going to see the questions doing just that. So we're still going to be working with our cards, our hand of cards, the 2,500,000 number. But we want to find a way of getting cards of more than one suit. So what is the complement of having more than one suit? All one suit, right? Not having more than one suit. So they'd all match. So the complement of this is having only one suit. Okay, or you could say all the same suit, whatever you wanted to do. Okay, but that's the description. We want them to be all matching. So they're all clubs, or they're all diamonds, or they're all spades, or they're all hearts. That's what we're looking for in that parenthesis part. So again, the number of ways that we get more than one suit is going to be the number of ways of getting anything to happen. That's that 2 million number, minus the number of ways of getting only one suit, or all of the same suit. So our any category is our 2,598,960. And to get all of one suit means first I have to pick the suit. So how many suits are there to pick from? 4. And how many am I choosing? 1. Okay, first I got to pick the suit. 4C1. And then I multiply that by getting all of them in that suit. So how many cards are in a suit? 13. And I'm going to choose all 5 of my cards to be of the same suit. This looks a lot like part 1. If you look back at your notes on 1, 13C5 matches. The part that's different is the 4C1. It's not picking a card, it's picking a suit. So 4C1 picks my suit, and then the 13C5 picks the cards that are in that suit. Okay, so this part at the beginning is going to stay here. And then I've got 4 factorial. I do choose 1 of them. I don't choose 3 of them. And then of my 13 factorial, I choose 5 of cards. I don't choose 8 cards. Okay, so there's 8 cards I don't pick, 5 cards I do pick. There's 1 suit I do pick, 3 suits I don't pick. That's where those denominators are coming from. And if we write these pieces out, this first one would be 4 times 3 factorial to cancel with the 3 factorial on bottom. So those cancel. And this one over here, I kind of would like to not write it all out again. I already did it. It's in the previous problem. We got that number. It was 1287. So this is coming from our previous problem, from problem number 1. So I'm going to end up with the number 4 from here times my 1287. So if you take 4 times 1287 and you subtract it from 2,598,960, what will you get?
2,593,812.
So 2 million, still almost 2,600,000, right? It's not changing it that much. Different hands of cards are going to have more than 1 suit. Not necessarily more than clubs, but more than 1 suit. All right, again, we're working on the structure of the language. How do we change and look for complements? So the rest of it's staying stationary, it's staying constant. We want the complement of having at least 1 face card. So what does that mean we don't want? Close. No face cards. I want to avoid saying number cards because it doesn't include the ace. That's the only reason I said that. If you included the ace as a number card in your mind, you could sort of think of it that way. That'd be all right. But this is having at least 1 face cards opposite, the logical opposite of that, the negation, the complement, is having no face cards. Okay, no face cards. So we have our same setup that we had before. The number of ways of getting at least 1 face card is the number of ways of getting anything to happen minus the number of ways of getting no face cards. Okay, so our number of ways of getting anything to happen is that same 2 million number, so I'm going to put that in there. How many cards are not face cards?
40.
40. How did you get that, Aubrey?
There's 12 face cards.
Okay,
And you do 52, which has all of them.
good. Okay, so you're still thinking it from an opposite perspective, which works really well for this description. There's 12 face cards. There's 52 cards total, so 52 minus the 12 would be my 40. Another way of doing that would be to simply count up what you do have, right? 2 through 10, there's 9 of them, plus the face card makes 10, so there's 10 of each suit. 10 times 4 would be 40, so you can do it either direction. So there are 40 cards to pick from, and I'm still creating a hand of 5 cards. Again, that's unique to this problem. We don't have to have hands of 5 cards in every problem. So if your problem said the same thing, but it does hands of 6 cards, make sure you're picking 6 cards, right? So be patient and aware as you're doing that, and don't rush through the problem too quickly. So on this then, we want 40 cards to pick from, and I'm going to pick 5 of them. So how many am I not picking? 35, right? So I'm going to have 40, 39, 38, 37, 36, and 35 factorial. And then on the bottom, I have that same 35 factorial that will cancel. And then I have 5, 4, 3, 2, and 1. Okay, so let's reduce some things. What can we reduce on bottom with something on top?
4 and 4.
Okay, we'll do one at a time. Go with yours first, Noelle.
You can do 2, 5, and 4 to get rid of the 40.
Okay, so the 5 and the 4 make 20. 20 times 2 would be 40. So if you want to gather all of those together and make out 4 and cancel out the 40, that's great. If you want to do it in pieces, that's fine too. What am I going to do with my 3? I have a couple options. What will 3 cancel with from top? 36, sure. So 3 and 36 makes 12. You also could have canceled it with 39 if you wish. Okay, so we're going to have the same 2 million number at the beginning. And then I need to multiply, let's see, what do we have? We have 39, 38, 37, and 12. If I have that one written down or not. I do. What do you get if you multiply those together? 39, 38, 37, and 12.
658,008.
Yep, 658,008. And if we subtract, we do finally get a number under 2 million. It's 1,940,952. So not much under 1 million, but these are the number of hands of cards or the number of ways I can get that hand if you wish. Okay, so I'll mention it again. Sometimes in my MathUp, when you get to these problems, it's going to actually put this in parentheses like this complement part, and it's going to tell you what the complement is. It will do that for you. Sometimes it's not, and you're just going to have to make that step yourself. Okay, you're going to have to figure out how do I do this with complements and make that decision yourself. Okay, I think I have one more of these. This one says at least one diamond. So, what is the complement? So at least one diamond means one or more, right? So I'd have to have 1 diamond, 2 diamonds, 3 diamonds, 4 diamonds, or 5 diamonds. This is the reason I don't want to do this, because I'd have to calculate 5 different combinations and add them together. I don't want to calculate 5 different combinations. I'd much rather do just one combination and subtract. Or even at worst case scenario, 2 combinations and subtract the 2 of them from one another if I had to. So what is the complement of having at least 1 diamond? No diamonds. Okay, so we're going to have the number of ways of getting at least 1 diamond. This is the number of ways of getting anything to happen, minus the number of ways of getting no diamonds. So the first part is the same as we've had, 2,598,960. Okay, so if I get no diamonds, that means I have to pick all cards that aren't diamonds. So how many cards are not diamonds?
Is it 39?
It is. And again, how'd you get 39?
52 and 13.
Right, so 13 of them are diamonds, which means the rest of them, of the 52, are not. So 52 cards minus the 13 diamonds would leave me with 39 cards that are not diamonds. Or, if you prefer, you can say there's 13 clubs and 13 spades and 13 hearts. And you can add the 13s together 3 times. You can think of it from sort of an addition perspective instead of subtraction perspective. And I'm choosing a 5-card hand still. So we have 39 factorial. I'm choosing 5, so how many am I not choosing? 34. So we'll write down our 39 till we get to 34. And then our 5, 4, 3, 2, and 1. So the 34s are going to cancel. 34 factorials are going to cancel. Okay, I can't go 5, 4, 2 like I did in the last one, so what do you want to cancel? Let's start with the 5. What are you going to cancel the 5 with? The 35. That's your only choice, right? So 5 and 35 give me a 7 here. Now what? 3 and 36, which we did before, so that gives me a 12. Now what? Let's do the 4 next. What about the 4? Don't overthink this, guys. It goes into the 12, exactly. We just dealt with the 12, so let's do it again. So the 4 will go into the 12, leaving me with a 3 here. And then what? Yeah, the 2 and the 38 will work. So 38 divided by 2 will give me what? 19. I have to kind of squeeze it in there, so try not to lose all your pieces like I am. We have a 39, a 19, a 37, a 3, and a 7. And what do I get if I multiply all those together?
5, 7, 5, 7, 5, 7.
Oh, that's such a nice number. look at that. The odometer on the car, my husband and I have 2 cars and we kind of switch driving them sometimes. The odometer on the red car that we have that was driving became 141414 this weekend. I took a picture. Fun numbers. 575757. And if I subtract these, what will I get? It's a fun number too, actually. Oh. 2023203. So it's still 2 million. 2,023,203 hands. Okay. So in terms of this section, when we started this section last class, I told you half of this section is hard stuff. That's the section we've done. The other half's actually really easy. Are you ready for the easy section? We all said absolutely, right? Absolutely ready for the easy section. Okay, so we're going to write down the definition, and then I'm going to describe to you why, at least in part, this is easy. So the additive principle of counting says if A and B are 2 sets, the number of items in A union B is the number of items in A plus the number of items in B minus the number of items in A intersect B, which you've seen before. That's not why I'm saying it's easy, but you have seen this before. We did this in set theory in chapter 2. If A and B are disjoint means they have nothing in common, okay, completely separated. Think Venn diagrams, 2 circles that don't overlap. Then the number of items in the union is simply the number of items in A plus the number of items in B. All right, I'm going to switch my slide to the directions for the next problem. And I would like for you to compare the way the problem or what the problem is asking, not the details of how to find it, but just what it's asking for compared to what we've been doing. Because what it's asking for is the reason why these problems are easier. Read through the question. Why should this be easier?
It's just asking how many there are.
It's asking how many there are, but we've been asked how many there are before. There's something else more to it.
It's not asking for any kind of like combination.
What's it asking for instead? One card. Look at it again. Do you see the word single in there? I'm not going to get a hand of cards. I'm getting one card. How many cards are there to pick from? 52, which means your answer cannot be bigger than 52. You with me? Okay. So if you're telling me some answer that's bigger than 52, you're thinking about the wrong thing because you're drawing a single card from a deck of 52. Drawing a single card is a whole lot easier than creating a handful of cards because you have to select a lot of them, right? Okay, everybody with me? So again, I'm doing this as an example because it lends itself so nicely to the things we've already sort of established as ground rules. Now, within the deck of cards, there's some things that overlap, and there's some things that don't. For example, a card cannot be both black and red, correct? But a card can be a diamond and an ace, right? So sometimes they're overlapping. That's that first equation. There is something in the intersection. There's a way to have both things happen at the same time. And sometimes there's no way for things to happen and have both be there at the same time. So of these two equations, the default equation that works for every problem is actually the first one. If I use the first equation and it happens to be that they never overlap, I just put a 0 in that last place. So this is the one that I'm going to be using on all of them, even if they're disjoint, simply because it can be used on all of them. Okay? So taking a look at our first one, I've already spoiled the fun a little bit, and I told you that you can have a diamond and an ace, right? It's called the ace of diamonds. That's what we call it. There is one card that's like that. So if I'm trying to draw a single card, what I'm actually trying to draw is I'm trying to draw or find the number of cards that are both a diamond, or that, not both, excuse me, that are a diamond or an ace. Okay, so I'll abbreviate it with sort of the letters when I can anyway, instead of writing them out. I want a diamond or an ace. And remember, we used the word or to represent, or we used the union to represent the word or when we did Venn diagrams, right? We're using it in the exact same way here again. And the way that this works is I find the number of diamonds, and I find the number of aces, and I subtract anything that is a diamond and an ace. Diamond and an ace. So, how many diamonds are there? 13. How many aces are there? 4. There's one of each suit, right? There's 4 aces. How many cards are a diamond and an ace? 1. There's exactly 1 card that is diamond and ace in that deck. So if I did 13 plus 4 and I subtract 1, what am I going to get? 16. Now think about that. If I pulled out all the diamonds and I set them in a pile, there'd be 13 of them, right? But within that 13, one of them is already an ace, right? One of them's an ace of diamonds. So all I got to do is go find the other 3 aces and stack them up with my 13. There should be 16. Even if I don't use my formula, I should be able to count just by physically taking them out of the deck and sticking them in my pile and get to 16. Okay? How about this one? Number card or a red card. So this is the number of ways I get a number card. This is not a hashtag. Just letting you know. I tell my children this all the time. I know. I'm not speaking to people who understand my language anymore. This is a number sign or a pound sign. Just so you know, it's not a hashtag. This is the number card or a red. So I want to get the number of ways of having a number card plus the number of ways of having a red card minus the number of cards that are both number cards and red. And again, if you don't like the U's and the unions and intersections, like that we're using those symbols, you can write the word or and in there. It's fine. And if it helps you to sort of think about them. How many number cards are there?
36.
36. How did you get to 36?
I just took the 13 of each suit and subtracted it by 4 of the face cards and the ace.
Okay, so that's how you did it. Okay, so what Jonah did is he said, okay, well, I'm going to count the things that aren't numbers. There's 4 in each suit that are not numbers. They're the 3 face cards and then my ace. So if I take those 4 times 4, because there's 4 suits, that's 16 out, then I would be left with 36 cards. That's one way to do it. Did anybody else think of it differently?
I just did 52 minus 12 minus 4.
Okay, so you did it in steps. So you took out the 12 face cards first and then took out the 4 aces second. Yes. And you could count them up directly too, right? 2 through 10. That's how many? 9 cards. There's 9 cards that are actually number cards, and there's 4 suits, so 9 times 4 would be 36. How many cards are red? 26. How many cards are both number cards and red cards? 18. How'd you get 18, Noelle?
There's 9 number cards and there's 2 red sets.
Okay, there's 9 number cards, 2 through 10, and there's going to be 9 of them that are hearts, that's red, and 9 of them that are diamonds, and that's red. So that's 18 total. So we've got 36 plus 26 minus 18. What would we get? 44. Numbers all smaller than 52, right? Numbers all smaller than 52. Okay, a couple more of these and we'll be done. A black card or a diamond. So we've got the number of cards that are black or diamond, which is the number of cards that are black, plus the number of cards that are diamond, minus the number of cards that are a black and a diamond. That's the formula. How many cards are black? 26. How many cards are diamond? 13. How many cards are black diamonds? None, right? Diamonds are red, unless you're in a ski slope. And then a black diamond actually exists, but it's not a card. Do you guys know that? Does anybody ski? Black diamonds is a run on a ski slope. All right, so we could have used that second formula on this one, right? Because these are disjoint sets. It can't be both black and diamonds at the same time. But it's also perfectly fine that I used the one that I highlighted in yellow and just put 0 in the last space. So 26 plus 13 minus 0 is 39. There are 39 cards that are either blacks or diamonds. In fact, the only thing that we didn't include is what? Hearts. And there's 13 of them, right? So you could also think of this sort of from a complements perspective if you chose to on this particular problem. All right, last one. Black or club. So the number of ways I get a black or a club. So I have my number of black cards plus my number of clubs minus my number of blacks and clubs. So how many black cards are there? I think we just did that one. 26. How many clubs are there? How many cards are black and club? 13. All the clubs are black, right? By sort of definition, that's how we have created them. So if I do 26 plus 13 minus 13, I get 26. There's 26 cards of this one.